Welcome to the sleepy cosmos. I invite you to close your eyes for a moment and imagine yourself drifting backward through time. You're floating past the noise of today's rushing world, past the rise and fall of civilizations, past the first tentative human footsteps on ancient soil. You're travelling back through millennia of seasons, through ice ages and warming periods, until you arrive at a young Earth, vibrant and untamed, spinning slowly in the cosmic dark like a blue jewel suspended in infinite space. As you float in this cosmic perspective, you can witness something profound, something that defies the gentle rhythm of everyday life and challenges your understanding of permanence. Not once, but 5 times in Earth's 4.5 billion year story, you would have watched life itself nearly vanish from existence. The thread of existence grew so thin it might have snapped forever, leaving the world you're observing as silent and barren as the dusty surface of the moon, with only wind and waves to mark the passing of empty days. Yet somehow, miraculously, life endured. If you had been there to witness these moments, you would have seen they weren't quick like lightning strikes that illuminate the sky for an instant. Instead, you would have watched them unfold over thousands, sometimes millions of years, like slow-motion catastrophes that tested every living thing. From the tiniest bacteria hiding in the deepest ocean vents, surviving on chemical energy alone, to the mightiest creatures walking the land, shaking the ground with every footstep. Tonight, as you settle into the quiet comfort of evening, as the day's worries begin to fade from your mind like mist in morning sunlight, you'll witness these great near endings alongside us. You'll drift through deep time like a leaf on a gentle current, visiting worlds so ancient they'll seem to you like half-remembered dreams from childhood. You'll see worlds where strange and wonderful creatures swam in warm seas covering entire continents, where forests of unfamiliar plants swayed under alien skies painted in colours beyond imagination. As you journey with us through each extinction, you'll discover stories of profound loss, yes, but also of unexpected hope and renewal. Because in every ending you witness, you'll find the seed of a new beginning, waiting patiently in the darkness. You'll watch life find ways you never expected, adapt in patterns that will seem almost magical to you, discover pathways through seemingly impossible circumstances, survive in places that should be completely hostile to existence itself. Stay with us until the end, because as you explore each of these 5 great extinctions, you'll uncover clues about how life endures, how it transforms, how it discovers pathways through darkness back into light. You'll first visit a time when the world you're observing was covered in shallow, crystal-clear tropical seas that sparkled under a sun younger than today's. You'll see creatures you can barely imagine living and dying in those warm waters, building massive coral reefs that stretched across entire continents like underwater cities you could explore. Then you'll watch as the ice came slowly, relentlessly, and everything changed in ways that would echo through millions of years. You'll witness the second great extinction, during a time when early forests were just learning to grow on land, their primitive roots reaching deep into soil for the very first time in the history you're observing. You'll see how the seas had become underwater gardens of life, teeming with armoured fish and coral reefs, then watch them gradually transform into silent graveyards, preserved in layers of black stone that you can still touch today. The third was the greatest dying our planet has ever known, a catastrophe so complete it nearly ended the story of life forever. Earth itself seemed to turn against every living thing, with massive volcanoes erupting continuously for thousands upon thousands of years, poisoning both air and water with deadly gases and acid rain. 9 out of every 10 species in the ocean simply disappeared, as if they had never existed at all. The fourth great extinction cleared the stage for giants to emerge from the shadows. When the volcanic dust finally settled, and the skies cleared after millions of years of chaos, dinosaurs stepped carefully into an emptied world and began to build an empire that would dominate every continent for more than 160 million years. The fifth and most recent extinction brought that magnificent dinosaur empire to a sudden and fiery end, when a mountain-sized asteroid fell from space like a cosmic bullet and plunged the entire world into darkness and winter that lasted for years, maybe decades. But here's what's truly beautiful and remarkable about these ancient stories. After each catastrophe, after each moment when life seemed completely finished forever, something wonderful and unexpected happened. Survivors emerged from hidden places like caves and deep burrows, from the ocean depths and high mountain refuges. Evolution began again with renewed creativity, more innovative than before, finding new forms, discovering new possibilities, inventing new ways to fill an empty world with beauty and wonder. We are part of this story. In your heartbeat lives the rhythm of ancient seas. In your breath moves the same air that once surrounded trilobites, scuttling across primordial seafloors, the same atmosphere that dinosaurs breathed as they walked through forests of giant ferns. The atoms in your body were forged in stars that died before our sun was born. They've been part of rocks and rain, plants and animals, cycling through Earth systems across billions of years. Some of those atoms lived through every one of these extinctions, carrying life forward from one age to the next. This is your invitation to a gentle journey through the deepest chapters of our planet's story. Not a tale of destruction, but of persistence. Not a story of endings, but of beginnings that emerge from endings. Not an account of death, but of life's endless creativity in the face of impossible odds. As we travel together through these ancient worlds, let the knowledge settle in your mind like sediment in still water. These extinctions teach us that life is both more fragile and more resilient than we ever imagined, more vulnerable to sudden changes, yet more persistent in the face of catastrophe than any story we could invent. Each extinction reset the world, clearing away the old to make space for the new, like sleep clearing away the thoughts of one day to make room for the dreams and possibilities of the next. If this calm voyage through deep time speaks to you, if these stories of ancient resilience bring you peace as you prepare for rest, a gentle like or subscribe helps guide more viewers to join us on this journey through Earth's most profound chapters. So settle back now, let your breathing slow, and prepare to witness something extraordinary. We're about to visit 5 moments when our planet walked to the very edge of silence, looked into the void, and somehow, always somehow, chose to continue. The story of life on Earth is your story too, and tonight, in the gentle darkness, we'll discover together how that story survived its greatest challenges, carrying forward the spark that eventually became you. Time carries us gently backward to a world 443 million years ago. As consciousness settles into this ancient moment, the Earth below looks nothing like the planet we know and love. There are no forests here, no flowers painting the landscape in familiar colours, no birds singing in trees, no familiar animals walking on dry land. Instead, we find ourselves floating in peaceful suspension above a world of endless shallow seas, warm as the most perfect bathwater, stretching from horizon to horizon under skies of pale amber and soft gold. Take a moment to orient in this alien yet beautiful world. The continents have not yet taken their familiar shapes. What will one day become North America and Europe are scattered puzzle pieces positioned near the equator. The climate is remarkably gentle and stable, warmer than any time in recent history, with no ice caps at either pole to chill the global atmosphere. This is the Ordovician period, and we're witnessing Earth's first truly magnificent experiment with complex life. Below our floating consciousness, the warm seas shimmer with an otherworldly beauty that would take your breath away if you had physical lungs to breathe with. These waters cover most of the continents, creating vast, shallow platforms that stretch for thousands of miles, perfect nurseries for life to flourish and experiment with new forms of existence. The sea temperature hovers around a comfortable 25 degrees Celsius, like a tropical lagoon that spans entire continents. There are no seasons as we know them, no winter ice or summer heat waves. The climate has remained stable for millions of years, creating perfect conditions for life to become increasingly complex and interconnected. As awareness drifts closer to the surface of these ancient seas, the remarkable inhabitants of this underwater paradise come into view. Strange and wonderful creatures move through this crystal clear water with purposes and patterns completely unlike anything in modern oceans. This is Earth's first great community of complex animals, magnificent in their utterly alien beauty, like living jewels scattered across an underwater landscape that sparkles in the eternal summer light. The water itself is so clear that visibility extends for hundreds of feet in every direction. There's no pollution here, no runoff from cities or farms, just pure seawater that filters the sunlight into gentle blues and greens. The extraordinary visibility allows observation of the intricate details of creatures that lived and died millions of years before our species even dreamed of existing. Trilobites scuttle across the seafloor like living jewels crafted by some cosmic artisan. Some are as small as a thumb, delicate and intricate as fine clockwork, others as large as dinner plates, impressive in their ancient majesty. Their compound eyes glitter like cut diamonds as they hunt for food in the warm shallows, each eye containing hundreds of individual lenses that give them a view of their underwater world that we can barely imagine. Close observation reveals their segmented bodies moving with perfect mechanical precision through the transparent water, their jointed legs working in coordinated waves as they navigate the complex seafloor landscape of coral gardens and algal mats. Some species have developed specialized feeding appendages that help them sift nutrients from the seafloor sediments, while others have become active predators, hunting smaller creatures with sophisticated sensory equipment. These remarkable trilobites have been evolving and perfecting their designs for over 100 million years by the time you're observing them, making them one of the most successful animal groups in Earth's history. They've become absolute masters of their underwater domain, developing compound eyes that can see underwater with incredible clarity and precision, sophisticated bodies that can roll up into perfect defensive balls when threatened, and highly sensitive chemical detectors that help them locate food sources in the murky sediments of the seafloor. Some trilobite species have even developed the ability to swim, using their flexible bodies to undulate through the water column like underwater butterflies. Others have become burrowers, creating elaborate tunnel systems in the seafloor sediments where they live protected lives, emerging only to feed on the rich organic matter that drifts down from the productive waters above. Swimming gracefully above the bustling trilobites, other creatures that would seem like pure science fiction in the modern world move through their liquid realm. Sea lilies wave in the gentle currents like underwater flowers blooming in slow motion, but they're actually animals, distant relatives of starfish and sea urchins that have chosen a completely different way of life. Their elegant stems root them firmly to the seafloor, while their feathery arms dance in the current, filtering microscopic particles of food from the nutrient-rich water flowing around them. These sea lily gardens stretch for miles across the seafloor, creating underwater forests of swaying, flower-like animals that provide shelter and hunting grounds for countless smaller creatures. Each sea lily is a marvel of biological engineering, with hundreds of tiny tube feet along its arms that create currents to bring food particles directly to its mouth. Giant sea scorpions patrol these ancient waters like underwater dragons, some longer than a grown person, their powerful bodies cutting through the water with surprising grace and efficiency. Despite their fearsome name, they're not actually scorpions at all, but distant relatives of spiders and horseshoe crabs that have adapted to life in the sea. These magnificent predators glide through their liquid world with predatory purpose, their paddle-like legs propelling them with smooth, powerful strokes as they hunt for smaller prey among the coral gardens and sea lily forests. These ancient predators possess compound eyes like their trilobite cousins, giving them excellent vision in the clear waters. Their front appendages have evolved into powerful grasping claws that can seize and manipulate prey with surprising dexterity. Some species have developed sophisticated chemical sensors that allow them to track prey through the water by following scent trails, much like bloodhounds following a scent through air. The most impressive builders in these seas are the corals and their relatives, ancient architects working on a scale that dwarfs any human construction project. You're witnessing the construction of Earth's first great reefs, massive limestone structures that stretch for hundreds of miles across the shallow seafloors, rising like underwater mountain ranges from the depths. These aren't quite like the colourful coral reefs of your modern world, but they serve the same crucial purpose, creating complex three-dimensional habitats where thousands upon thousands of species can live together in intricate ecological relationships. These ancient reef builders work slowly but relentlessly, each polyp secreting calcium carbonate to build its tiny cup-shaped home. Over millions of years, these individual efforts combine to create structures visible from space, if there were anyone in space to see them. The reefs provide shelter for small creatures, hunting grounds for predators, and surfaces for countless filter feeders to attach themselves and harvest nutrients from the flowing water. As observation continues of this thriving underwater world from a timeless vantage point, its profound stability and deep harmony become apparent. This ecosystem has been developing and refining itself for millions upon millions of years, with each species finding its perfect niche in the underwater community. The climate has remained warm and steady for longer than the mind can easily comprehend. Ocean chemistry has stayed constant, with the perfect balance of minerals and nutrients to support this explosion of life. The sea level has remained stable, keeping these vast shallow platforms submerged at just the right depth for life to flourish. Life has found a rhythm here in these endless shallow seas, a complex balance of predator and prey, filter feeder and decomposer, builder and burrower that seems like it could continue unchanged forever. Energy flows through the ecosystem in well-established patterns. Nutrients cycle efficiently from living creatures to dead organic matter, and back to living creatures again. It's a world in perfect biological equilibrium. But as the journey through time continues, allowing thousands of years to pass in moments, subtle changes begin creeping into this perfect world. At first, the changes are almost imperceptible, slight shifts in temperature and current patterns that only the most sensitive creatures might detect. Then, gradually, the changes become more dramatic and impossible to ignore. This marks the beginning of the end of this ancient underwater paradise, though the creatures living through it have no way to understand what's happening to their world. The changes unfold over timescales far longer than any individual lifetime, so each generation experiences conditions only slightly different from their parents, never realizing they're part of a world-ending transformation. We're witnessing the beginning of the end of this ancient world, though the process will unfold over hundreds of thousands of years. Far to the south, beyond the tropical seas where we're peacefully floating, something unprecedented and world-changing is happening. A massive ice sheet is beginning to form on the southern continent of Gondwana, starting as seasonal snow that fails to melt completely during the brief summers, then accumulating year after year into permanent glacial ice. The planet's climate system, which has remained stable and predictable for so many millions of years, is beginning to tip toward a completely new state. Scientists would later call this the Andean-Saharan glaciation, but from our perspective it simply appears as the slow emergence of a white, frozen wasteland where warm land used to be. The ice grows slowly at first, almost imperceptibly. But ice has a way of feeding on itself. The white surface reflects sunlight back to space, instead of absorbing it. The more ice that forms, the cooler the planet becomes. The cooler the planet becomes, the more ice can form. From our vantage point in time, this process can be observed unfolding over thousands of years. The ice sheet spread across the southern continent like a slow-motion avalanche. Glaciers flow toward the sea, carving icebergs the size of islands into the increasingly cold southern oceans. As the ice spreads, the the sea level begins to drop. All that water being locked up in ice has to come from somewhere, and it comes from the oceans. The vast shallow seas that have been home to the trilobites and sea lilies and corals begin to shrink. This is catastrophic for the creatures we've been observing. These animals are adapted to life in shallow, warm seas. As the water level drops, their habitat simply disappears. Vast areas of sea floor that were once covered by miles of life-giving water are suddenly exposed to air for the first time in millions of years. Entire ecosystems become stranded. Coral reefs that took millions of years to grow find themselves high and dry. Trilobites that need the shallow seas to filter their food are trapped in isolated pools that grow smaller and saltier each day. The sea lilies, rooted to the seafloor, can only wait helplessly as the water recedes around them. But the dropping sea level is only the beginning of this crisis. As observation continues, it becomes apparent that the chemistry of the remaining seas is beginning to change in deadly ways. The Ice Age has disrupted ocean currents that have flowed the same way for millions of years. Deep oxygen-poor water begins to rise to the surface, poisoning the shallows where most life exists. This marks the development of ocean anoxia, one of the most deadly conditions that can affect marine life. The word anoxia means without oxygen, and that's exactly what's happening to these ancient seas. The water that once sparkled with life is turning dark and lifeless. This oxygen depletion happens gradually, over thousands of years, but it's relentless. The remaining sea life struggles to survive in water that can no longer support them. Fish gasp at the surface, seeking oxygen that's no longer there. Bottom-dwelling creatures like the trilobites find their world becoming uninhabitable. The lack of oxygen also allows dangerous bacteria to thrive. These microbes produce hydrogen sulfide, a poison that turns the water toxic to most other forms of life. The seas that were once crystal clear become murky and deadly. From our perspective in deep time, this crisis unfolds in two distinct phases, though they blend together over the millennia. First comes the glaciation and the dropping sea levels. This eliminates most of the shallow sea habitats where life flourished. Then comes the warming phase as the ice begins to melt. But this brings its own problems. As the ice sheets finally begin to retreat, life might be expected to recover quickly. But the returning seas are poisoned by the anoxic conditions. The warm water that floods back onto the continental shelves carries with it the chemical signature of death: low oxygen, high acidity, and toxic gases. We're witnessing what scientists would later call the late Ordovician mass extinction, though from this perspective it's simply the slow death of a world. This crisis will eliminate about 85% of all species in the ocean. Entire groups of animals that have thrived for millions of years will disappear forever. The trilobites, those successful arthropods you watched scuttling across the seafloor, are devastated. Many species vanish completely. The great coral reefs collapse into rubble. The sea lilies that waved like underwater gardens are reduced to scattered fragments. But even as we witness this destruction, signs of hope become apparent. Life is remarkably resilient, and even in the midst of this catastrophe, some creatures find ways to survive. They retreat to refuges where conditions remain tolerable, deeper waters that still hold oxygen, isolated seas that maintain their chemistry, or simply by going dormant until better times return. These survivors will inherit a changed world. As the ice finally melts completely and the seas return to something like their former extent, new opportunities emerge. The empty niches left by the extinct species become laboratories for evolution. New forms of life begin to experiment with different ways of living in the recovering seas. We're observing one of the most important lessons that Earth's history teaches, that endings and beginnings are intimately connected. This extinction, devastating as it is, clears the way for new experiments in living. The survivors will diversify and adapt, eventually creating ecosystems even more complex and beautiful than what came before. Time flows forward like a gentle river carrying memories and dreams, taking us 100 million years beyond the icebound world of the Ordovician crisis. The Earth has transformed itself once again, healing completely from that ancient catastrophe and blossoming into something entirely new and magnificent. We arrive now in the late Devonian period, 372 million years ago, when our planet has become a warm, lush paradise, unlike anything seen before or since in Earth's long history. The world spreads before us in breathtaking abundance and diversity. Vast tropical seas stretch across entire continents, their waters crystal clear and bathed in perpetual golden sunlight from a sun that never seems to set on this ancient summer. The global climate is remarkably stable and warm, with atmospheric carbon dioxide levels much higher than in modern times, creating a natural greenhouse effect that maintains tropical conditions even at the poles. The world spreads before us in magnificent abundance. Vast tropical seas stretch across continents, their waters crystal clear and bathed in golden sunlight. But these are not the empty seas of the ancient Ordovician world. These waters teem with life that has grown bold and experimental over millions of years of evolution, creating underwater cities of unprecedented complexity and stunning beauty. The diversity of marine life has exploded beyond anything previously imagined, with ecological niches filled by creatures that seem almost too fantastic to be real. The continental shelves have become underwater gardens where life experiments with every possible form and function. Brachiopods carpet vast areas of the seafloor like living tiles, their shells filtering nutrients from the water in perfectly coordinated communities. Crinoids, those flower-like relatives of starfish, create underwater meadows that sway gracefully in the gentle currents, their stems sometimes growing over 100 feet tall. Massive coral reefs rise from the seafloor like natural cathedrals built by millions of tiny architects, some growing hundreds of feet tall and stretching for thousands of miles across the continental shelves in continuous barriers that dwarf even modern reef systems. These are not the simple reef builders of the ancient past, but sophisticated organisms creating structures so complex and beautiful they rival anything in the modern world, serving as both home and hunting ground for countless species. These Devonian reefs represent a pinnacle of biological architecture. Tabular corals spread their flat, table-like forms across vast areas of the seafloor, creating platforms where other organisms can build their own communities. Rugose corals construct elaborate horn-shaped homes that spiral toward the surface in elegant towers, some reaching heights of several feet and housing complex internal chambers where the living polyps filter food from the flowing water. Swimming through these reef cities are creatures that would astound any modern observer with their alien beauty and impressive adaptations. Armored fish patrol the coral gardens like underwater knights, their bodies encased in thick, bony plates that gleam like polished metal in the filtered sunlight streaming down from above. These placoderms, as scientists would later name them, represent one of evolution's most successful experiments in defensive armor, with some species developing articulated joints in their armor that allow surprising flexibility despite their heavy protection. Some of these ancient fish grow to truly enormous sizes that dwarf most modern marine predators. Dunkleosteus, the undisputed apex predator of these Devonian seas, stretches 30 feet from nose to tail, its massive jaws lined not with teeth, but with sharp, shearing plates of bone that can exert a bite force of over 5,000 pounds per square inch. These bone shears work like giant scissors, capable of crushing almost anything unfortunate enough to encounter them, including other armoured fish and even sharks. These armoured giants share their world with countless smaller marvels that fill every possible ecological niche. Primitive sharks glide through the water with smooth, predatory efficiency, already perfecting the streamlined body plan that will serve their descendants for hundreds of millions of years to come. Early ray-finned fish experiment with new ways of swimming and feeding, their fins beginning to develop the intricate ray structure that will eventually dominate the world's waters and give rise to most modern fish species. Ammonoids, those spiral-shelled relatives of modern squid and octopus, jet through the water using primitive versions of the propulsion systems their descendants will perfect. Their coiled shells, divided into chambers for buoyancy control, make them among the most sophisticated swimmers in these ancient seas. Some species develop shells as large as truck tires, while others remain small and delicate, their shells ornamented with intricate ribs and spines. But perhaps the most revolutionary change is happening not in the seas, but on the land high above them. For the first time in Earth's entire history, true forests are taking root and spreading across the continents with unprecedented speed and ambition. These are not the small, tentative plants that first colonized the land after the Ordovician extinction, but towering trees that reach toward the sky with evolutionary boldness that transforms entire landscapes. Vast forests of primitive conifers, tree ferns and early seed plants stretch from horizon to horizon, their canopies creating the first great woodland ecosystems our planet has ever known. Some individual trees grow over 100 feet tall, their massive trunks supported by root systems that penetrate deep into bedrock. These forests represent nothing less than a complete revolution in how life interacts with the planet itself, changing the very face of the continents and the chemistry of the atmosphere. Vast forests of primitive conifers and ferns stretch from horizon to horizon, their canopies creating the first great woodland ecosystems on Earth. Some trees grow over 100 feet tall, their massive trunks supported by root systems that penetrate deep into the soil. These forests represent a revolution in how life interacts with the planet itself. The roots of these ancient trees are literally changing the very chemistry and geology of the Earth in ways that will have profound consequences for all life. As they reach deep into bedrock searching for minerals and water, they accelerate the weathering of rocks at rates never before seen in planetary history, releasing vast quantities of nutrients into the soil. These chemical changes affect not just the local soil, but the entire global system of nutrient cycles that connect land, sea, and atmosphere. Rain falling on these vast forests picks up these newly released nutrients and carries them in an endless network of rivers and streams toward the waiting seas, creating a massive pipeline of fertilizer flowing from the continents into the oceans. This represents a fundamental shift in the planet's nutrient cycles that will have consequences lasting for millions of years. This represents a fundamental shift in the planet's nutrient cycles. For the first time, massive amounts of phosphorus and nitrogen are being washed from the land into the oceans. The seas, which have been relatively nutrient poor for millions of years, suddenly find themselves enriched with fertilizers that promote explosive growth of marine life. At first, this massive enrichment seems like a magnificent gift from the land to the sea, a bountiful offering that should support even greater diversity and abundance of marine life. Phytoplankton populations explode in the newly fertilized waters, creating the base of food webs more complex and productive than anything previously seen in Earth's history. The increased productivity supports larger populations of everything from the smallest filter feeders to the greatest predators, and for a time, the Devonian seas seem to be entering a golden age of biological abundance. But nature's gifts often come with hidden costs that only become apparent over long periods of time, and this one proves to be no exception to that ancient rule. The same nutrients that feed the spectacular phytoplankton blooms also feed bacteria and other decomposers in the deep waters and sediments. When the massive plankton blooms inevitably die and sink to the seafloor in organic blizzards, they create equally massive populations of bacteria that consume dissolved oxygen as they break down the organic matter. The process begins slowly, almost imperceptibly. The clear waters of the tropical seas start to develop a subtle greenish tinge. The change is so gradual that it would be barely noticeable to creatures living through it, but from our perspective in deep time, we can see the transformation unfolding like a slow-motion catastrophe. Algae blooms begin to appear with increasing frequency across the shallow seas. These aren't the small, localized blooms that modern oceans experience. but massive events that can cover thousands of square miles of ocean surface. When these blooms die, they sink to the bottom in vast organic snowstorms, carpeting the seafloor with decaying matter. The bacteria that decompose this organic rain consume oxygen faster than it can be replenished. The deep waters of the oceans, already poorly oxygenated due to the warm global climate, begin to develop dead zones where almost nothing can survive. These anoxic waters are not just lacking in oxygen, they actively produce toxic hydrogen sulfide gas that poisons any remaining life. The crisis deepens over hundreds of thousands of years, progressing through what scientists would later identify as distinct phases. The first major pulse, known as the Kellwasser event, strikes the marine ecosystems like a slow-acting poison. The beautiful coral reefs that took millions of years to build begin to die back as the water chemistry changes around them. The great armoured fish that rule these seas find their world becoming increasingly hostile. Many species simply disappear, unable to adapt to the changing conditions quickly enough. The reef ecosystems that supported such incredible diversity collapse into rubble, leaving behind only the hardy generalists that can tolerate the new conditions. But this is not a quick catastrophe, like an asteroid impact or a massive volcanic eruption. This is a slow strangulation that unfolds over geological time. The Devonian seas don't die suddenly. They fade gradually like a sunset that lasts for millennia. The second major pulse, the Hangenberg event, delivers what might be considered the final blow. Ocean anoxia spreads even further, and the toxic conditions that were once confined to deep waters begin to creep up onto the continental shelves where most marine life makes its home. From our vantage point in time, we can observe how this extinction differs from the dramatic icebound crisis of the Ordovician. There are no glaciers here, no dropping sea levels, no sudden climate shifts. Instead, this is a crisis of abundance turned toxic, of life's own success becoming its downfall. The forests that seem to be Earth's crowning achievement become, in a sense, agents of destruction. Their gift of nutrients to the sea creates conditions that ultimately suffocate much of the marine life they were meant to nourish. It's a sobering reminder that in Earth's complex systems, even beneficial changes can have unintended consequences. Yet even as we witness this slow-motion catastrophe, we can see signs of hope and resilience. Life does not simply surrender to these changing conditions. In the toxic, oxygen-poor waters, new forms of bacteria thrive, finding ways to live without oxygen, or even using the poisonous hydrogen sulfide as an energy source. These microbial communities may seem primitive, but they're performing the essential work of breaking down organic matter and gradually restoring the ocean's chemistry. Some marine creatures find refuge in the few areas where oxygen levels remain adequate. Others evolve rapidly, developing new physiological adaptations that allow them to survive in the changing conditions. The survivors of this crisis will carry life forward into the next chapter of Earth's story. The recovery from the late Devonian extinction is slow but steady. As the massive forest ecosystems mature and stabilize, the rate of nutrient runoff gradually decreases. The ocean chemistry begins to return to more balanced conditions. Oxygen levels slowly rise as the organic matter in the sediments becomes buried and stops consuming oxygen from the water column. In the recovering seas, new ecosystems begin to emerge. The simple reef systems that replace the complex Devonian reefs may lack the diversity of their predecessors, but they represent a new beginning. Evolution begins again, the patient work of building complexity from simplicity, diversity from uniformity. This ancient crisis teaches us profound lessons about the interconnectedness of Earth's systems. The atmosphere, the oceans, the land, and life itself are all part of a single, integrated system. Changes in one component inevitably affect all the others, sometimes in ways that take millions of years to fully manifest. The late Devonian extinction reminds us that even positive developments can have negative consequences when they occur too rapidly for Earth's systems to adjust. The evolution of forests was undoubtedly one of the most important developments in our planet's history, but their initial impact on ocean chemistry created conditions that many marine species simply could not survive. As we prepare to move forward through time to witness the next great crisis in Earth's long history, we carry with us this profound lesson about the delicate balance that exists between all of Earth's interconnected systems. The late Devonian world, with its lush forests and gradually dying seas, shows us how beauty and catastrophe can exist side by side, how life's greatest achievements can carry within them the seeds of its greatest challenges and transformations. Yet through it all, life demonstrates its incredible persistence and creativity. The survivors of this ancient crisis carried forward the precious genetic legacy that would eventually give rise to all the diversity we see in modern oceans and forests. In their quiet persistence through seemingly impossible conditions, we can see reflected the same fundamental resilience that flows through every living thing, including ourselves, connecting us across the vast depths of time to these ancient seas where life learned once again to endure and overcome. Now we move onward like a slow river through the deepest channels of history, carrying us forward another 120 million years from the recovering Devonian seas. We arrive now at the end of the Permian period, 252 million years ago, when Earth has reached perhaps the greatest crescendo of life in its entire 4 billion year history. This is a world that pulses with abundance and diversity, a planet where life has experimented with every possible form and successfully filled every conceivable ecological niche, from the deepest ocean trenches to the highest mountain peaks. The Earth stretches before us in magnificent diversity and breathtaking complexity. All the continents have drifted together through the slow dance of plate tectonics to form a single, massive supercontinent called Pangaea, surrounded entirely by the vast Panthalassic Ocean. This unique arrangement creates climates and ecosystems unlike anything in the modern world, with vast inland areas experiencing extreme seasonal variations and temperature swings, while coastal regions enjoy more moderate and stable conditions. On land, life has achieved a level of sophistication and complexity that would not be seen again for millions of years to come. Vast forests of conifers and early seed plants stretch across entire continents, their towering canopies reaching toward the sky in cathedral-like groves that filter sunlight into dappled patterns on the forest floor. These are not the simple, experimental forests of earlier geological periods, but mature, complex ecosystems supporting an incredible diversity of life forms that fill the air with flying insects, populate the forest floor with scurrying creatures, and occupy every possible layer in between, from the canopy to the root systems. These ancient woodlands represent the culmination of millions of years of plant evolution. Massive conifers develop sophisticated root systems that allow them to grow to unprecedented heights, while early flowering plants begin their first tentative experiments with the pollination strategies that will eventually transform terrestrial ecosystems. The understory is rich with ferns, cycads, and other primitive plants that create a lush green world of incredible beauty and productivity. Strange and wonderful creatures inhabit these ancient woodlands in numbers and varieties that boggle the imagination. Early reptiles have diversified into forms that hint at all the major groups that will follow in later geological periods. Some have become large, powerful herbivores, using their specialized jaws and grinding teeth to crop the tough, fibrous vegetation of this ancient world. Others have evolved into swift, agile predators, their bodies perfectly designed for hunting through the dense undergrowth and pursuing prey across open glades. The insect life of this period is particularly spectacular, with dragonflies sporting wingspans measured in feet rather than inches, and cockroaches the size of dinner plates scurrying through the leaf litter. These giant arthropods thrive in the oxygen-rich atmosphere of the Permian, which contains significantly more oxygen than our modern air, allowing them to grow to sizes that would be impossible today. Among the most remarkable and evolutionarily significant inhabitants of this Permian world are the synapsids, our own distant ancestors who represent the lineage that will eventually give rise to all mammals. These mammal-like reptiles have developed many of the key innovations that will later characterize mammals: specialized teeth designed for different types of food processing, improved hearing systems that allow for better communication and predator detection, and even the earliest beginnings of hair-like structures for insulation and temperature regulation. Some species, like the massive and impressive Astemonosuchus, sport elaborate horns and bony crests that would look fantastic and alien even by modern standards, while others develop the first primitive versions of the warm-blooded metabolism that will become characteristic of their mammalian descendants. The seas of this ancient world teem with life that rivals any period in Earth's entire history for sheer diversity and abundance. Coral reefs have not only recovered from the earlier Devonian crisis, but have expanded and evolved beyond their predecessors, creating underwater cities of incredible architectural complexity and biological richness. These reef systems support vast communities of brachiopods, crinoids, bryozoans, and other filter feeders that carpet enormous areas of the seafloor in living tapestries of colour and movement. The marine food webs of the Permian are intricate beyond description. Microscopic plankton supports small filter feeders, which in turn support larger predators in an unbroken chain that extends from the tiniest bacteria to the largest marine reptiles. The ocean chemistry is perfectly balanced to support calcium carbonate formation, allowing shell-building organisms to construct elaborate and beautiful forms. Swimming through these reef systems are creatures both familiar and utterly strange to modern eyes. Sharks patrol the waters much as they do today, their basic body plan already perfected through millions of years of evolution for their predatory lifestyle. But sharing the seas with them are animals that have no modern equivalents: bizarre armoured fish with intricate bony plates, spiral-shelled ammonoids the size of car tyres that jet through the water using primitive propulsion systems, and countless other experimental forms that evolution has tried and tested in this great laboratory of life. The ammonoids in particular represent one of the most successful groups of marine predators ever to evolve. Their coiled shells, divided into chambers for precise buoyancy control, make them incredibly sophisticated swimmers capable of rapid movement and complex hunting behaviours. Some species develop shells with intricate ribbing and ornamentation that rivals the most elaborate human artwork. This is a world that seems to have reached a perfect balance, a culmination of nearly 4 billion years of evolutionary experimentation. Life has learned to live everywhere, in the deepest oceans, on the highest mountains, in the driest deserts, and in the most toxic environments. The biosphere has achieved a complexity and stability that suggests it could continue unchanged for millions more years. But even as we observe this magnificent world at its peak, subtle changes are beginning beneath the surface. Deep within the Earth, forces are stirring that will transform this paradise into the closest thing to hell that our planet has ever experienced. In what will one day be Siberia, massive chambers of magma are building pressure beneath the Earth's crust. This is not the localized volcanism that has affected the planet before, but something unprecedented in scale and duration. The Earth itself is preparing to unleash a catastrophe that will dwarf anything previously seen. The first signs of this coming disaster appear as isolated volcanic eruptions scattered across the Siberian landscape. At first, these seem like ordinary volcanic activity, the kind that has always been part of Earth's geological processes. Local ecosystems are disrupted, but life adapts and recovers as it always has. But these initial eruptions are merely the prelude to something far more catastrophic. Deep beneath Siberia, a massive plume of superheated rock is rising from the Earth's core mantle boundary, carrying with it the energy to reshape the entire planet's surface. When this plume finally reaches the surface, it unleashes the Siberian Traps, one of the largest volcanic events in Earth's history. This is not a single eruption, but a sustained outpouring of lava that will continue for hundreds of thousands of years, covering an area larger than the entire European continent with molten rock. The scale of this volcanism defies imagination. Lava flows stretch for hundreds of miles, creating rivers of molten rock that bury entire ecosystems beneath layers of basalt. The eruptions pump enormous quantities of toxic gases into the atmosphere: sulfur dioxide that will create acid rain, carbon dioxide that will drive catastrophic climate change, and hydrogen sulfide that will poison the air itself. As the volcanism continues year after year, decade after decade, the effects begin to cascade through Earth's interconnected systems. The massive injection of greenhouse gases into the atmosphere drives global temperatures upward at a rate that few ecosystems can tolerate. Acid rain falls from skies choked with volcanic ash, poisoning the soil and water that support terrestrial life. The oceans begin to change in ways that spell doom for marine life. The warming atmosphere heats the surface waters, reducing their ability to hold dissolved oxygen. At the same time, acid gases from the volcanoes make the seawater increasingly acidic, creating conditions that dissolve the shells and skeletons of countless marine organisms. But perhaps the most deadly change occurs in the ocean's circulation patterns. The warming climate disrupts the currents that normally bring oxygen-rich water to the deep sea. Instead, the deep waters become increasingly stagnant and toxic, producing hydrogen sulfide gas that bubbles up to poison the surface waters where most marine life exists. The beautiful coral reefs that took millions of years to build begin to dissolve in the acidic waters. The diverse communities of brachiopods and other filter feeders find their shells literally dissolving around them. Fish struggle to breathe in water that contains less and less oxygen each year. On land, the effects are equally devastating. The acid rain strips leaves from trees and poisons the soil that supports plant life. The rising temperatures stress ecosystems already struggling with the toxic atmosphere. Many of the magnificent forests that characterize the Permian world begin to wither and die, leaving behind barren landscapes that look more like alien worlds than the lush paradise they once were. This is not a quick catastrophe like an asteroid impact, but a slow strangulation that unfolds over hundreds of thousands of years. Each generation of organisms faces conditions slightly worse than their parents experienced, never quite understanding that they are living through the end of their world. The crisis reaches its peak during what geologists call the end-Permian extinction event, though event hardly seems adequate to describe something that unfolds over such vast timescales. This is the Great Dying, the most severe extinction crisis in Earth's entire history. By the time the worst of the crisis has passed, the statistics are almost incomprehensible. Approximately 90% of all marine species have vanished forever. On land, the devastation is nearly as complete, with roughly 70% of terrestrial species eliminated. Entire groups of organisms that dominated the Permian world simply disappear from the fossil record, as if they had never existed. The trilobites, those successful arthropods that survived the earlier Ordovician and Devonian crises, finally meet their end. These ancient survivors, which had persisted for nearly 300 million years, cannot withstand the combination of ocean acidification, anoxia, and toxic gases that characterize the end-Permian crisis. Many of the magnificent synapsids that represented our own evolutionary lineage also disappear during this time. The elaborate horned forms like Asteminosuchus vanish, along with most of the large herbivores and predators that made the Permian forests so diverse and complex. In the seas, the great reef ecosystems collapse entirely. The brachiopods that had dominated marine environments for hundreds of millions of years are reduced to a handful of surviving species. The spiral-shelled ammonoids, though they will eventually recover, are pushed to the very brink of extinction. For a brief moment in Earth's history, it seems as though the planet might become permanently lifeless. The combination of toxic atmosphere, acidic oceans, and extreme temperatures creates conditions that approach the limits of what life can tolerate. Our planet teeters on the edge of becoming another Venus. a world where the greenhouse effect has run away completely. But even in this darkest chapter of Earth's story, life demonstrates its remarkable resilience. In a few refugees where conditions remain tolerable, survivors persist through the crisis. Some find shelter in caves where the toxic atmosphere cannot reach them. Others survive in isolated bodies of water that maintain more favourable chemistry. Still others simply go dormant, waiting for better times to return. These survivors represent the genetic bottleneck through which all subsequent life must pass. Every organism alive today, from the smallest bacteria to the largest whales, traces its lineage back to ancestors that somehow endured the Great Dying. In their survival lies the seed of all future diversity. The recovery from this catastrophe is slow and fragile, measured not in thousands but in millions of years. As the Siberian volcanism finally subsides, the Earth's climate system begins the long process of returning to more stable conditions. The toxic gases in the atmosphere are gradually removed by chemical reactions with rocks and seawater. The ocean circulation slowly recovers, bringing oxygen back to the deep waters. In this recovering world, evolution begins again the patient work of rebuilding complexity from simplicity. The few surviving species begin to diversify, exploring the empty niches left by the extinct forms. New ecosystems emerge, different from what came before but beautiful in their own way. The Permian extinction teaches us profound lessons about the interconnectedness of Earth's systems and the limits of planetary resilience. It shows us that even the most stable and diverse ecosystems can be pushed beyond their breaking point when multiple stresses combine in unfortunate ways. Yet it also demonstrates life's extraordinary ability to persist through seemingly impossible conditions. The survivors of the Great Dying carried forward the genetic heritage that would eventually give rise to dinosaurs, mammals, flowering plants, and all the diversity we see in the modern world. As we prepare to move forward through the vast corridors of time to witness the next chapter in Earth's remarkable recovery, we carry with us this profound lesson about resilience in the face of ultimate catastrophe and the power of life to endure. The Great Dying reminds us that even when the world seems to be ending completely, even when conditions become almost incompatible with life itself, existence finds a way to continue, to adapt with incredible creativity, and eventually to flourish once again in forms more beautiful than before. Now we drift 50 million years beyond the devastated world of the Great Dying. We arrive now in the late Triassic period, 201 million years ago, when Earth has spent countless millennia healing from its greatest wound and blossoming into something entirely new and magnificent. This is a world reborn from catastrophe, where life has not merely recovered, but has invented forms and possibilities that never existed before. The planet spreads before us in lush, verdant abundance that would seem like paradise to any observer. The supercontinent Pangaea still dominates the global geography, but subtle changes are beginning as the first cracks appear in this massive landmass. These early rifts hint at the Atlantic Ocean that will one day separate the Americas from Europe and Africa, though that separation lies far in the future. The climate of this Triassic world is warm and humid across most of the planet, with no ice caps to chill the polar regions and no extreme seasonal variations to stress the ecosystems. Atmospheric carbon dioxide levels remain elevated from the Permian volcanism, creating a natural greenhouse effect that maintains tropical conditions even at high latitudes. This warmth and stability have allowed life to explore evolutionary possibilities that were impossible during the harsh recovery period. Vast forests stretch across the continents in green waves that seem to roll on forever. These are not the experimental woodlands of the early Triassic, but mature, sophisticated ecosystems that represent life's renewed confidence in its ability to dominate the terrestrial environment. Conifers have grown to enormous sizes, their trunks sometimes reaching diameters of 10 feet or more, and their crowns forming canopies hundreds of feet above the forest floor. Among these towering conifers grow tree ferns of incredible beauty and complexity, their fronds creating delicate patterns of light and shadow on the forest floor below. Early cycads experiment with new, reproductive strategies, developing the large, colourful seed cones that will eventually inspire the evolution of flowering plants. Although the understory is rich with ferns, horsetails, and other primitive plants that create a lush, green world reminiscent of a tropical paradise. But perhaps the most remarkable inhabitants of these Triassic forests are the dinosaurs, though they are still relatively small and humble creatures sharing their world with many other groups of reptiles. Early dinosaurs like Paleontology move through the forests on swift, bird-like legs, hunting smaller prey with intelligence and coordination that hints at the magnificent future awaiting their lineage. These early dinosaurs are not yet the giants that will dominate later periods, but they possess innovations that give them significant advantages over their competitors. Their upright posture allows for more efficient locomotion than the sprawling gait of other reptiles. Their sophisticated respiratory systems provide the oxygen efficiency needed for active lifestyles. Most importantly, their reproductive strategies and parental care behaviours suggest a level of behavioural complexity that sets them apart from their contemporaries. Sharing the Triassic world with these early dinosaurs are many other groups of reptiles that experiment with different approaches to terrestrial life. Etosaurs develop elaborate armour plating that makes them look like living tanks as they browse on the abundant plant life. Phytosaurs evolve long, crocodile-like snouts for fishing in the rivers and lakes that wind through the forested landscapes. Perhaps most impressive are the Rauisuchians, massive predators that grow to lengths of over 30 feet and dominate the Triassic food webs as apex hunters. These formidable reptiles possess powerful jaws filled with razor-sharp teeth and limbs capable of supporting their enormous bulk while maintaining surprising agility. For a time, it seems as though they, rather than the dinosaurs, might inherit the Earth. The diversity of Triassic life extends far beyond the reptiles. Early mammals, descended from the synapsid survivors of the Permian extinction, begin their long evolutionary journey toward the forms that will eventually dominate the post-dinosaur world. These proto-mammals are still small and secretive, living in the shadows of the great reptiles, but they possess innovations in metabolism, reproduction, and behaviour that will serve their descendants well. In the seas, life has also recovered magnificently from the Permian catastrophe. New forms of coral have evolved to replace those lost in the Great Dying, creating reef systems that rival anything from the past. Marine reptiles have diversified into forms both familiar and strange, from long-necked plesiosaurs that patrol the open oceans to armoured placidonts that crunch shellfish in the shallow seas. The ammonoids, those spiral-shelled cephalopods that barely survived the Permian extinction, have rebounded with explosive diversity. Their shells develop increasingly elaborate forms and ornamentation, creating some of the most beautiful fossils in the geological record. These creatures become so abundant and diverse that their fossils serve as index species for dating Triassic rocks around the world. This magnificent Triassic world seems to have achieved a new stability after the chaos of the Permian recovery. Ecosystems have had tens of millions of years to mature and develop complex interdependencies. Food webs have become intricate networks that efficiently cycle nutrients and energy through multiple trophic levels. The climate has remained stable and favourable for millions of generations. But even as we observe this apparent paradise, subtle changes are beginning deep within the Earth that will once again test life's resilience. As Pangaea starts its slow breakup, enormous geological forces are building that will reshape not only the continents, but the entire global environment. The initial signs of change appear as increased volcanic activity scattered across what will become the Atlantic basin. At first, these eruptions seem unremarkable, the kind of localized geological activity that has always been part of Earth's natural processes. But these early volcanic events are merely the harbingers of something far more dramatic and potentially catastrophic. Deep beneath the Earth's surface, a massive plume of superheated rock is rising from the core mantle boundary, carrying with it the energy to split continents and transform global climate. This plume will eventually create the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history, though its full impact will not be felt for thousands of years. As the late Triassic period draws to a close, the first major volcanic eruptions begin in earnest. Unlike the gradual localized volcanism that has characterized most of Earth's history, these eruptions release enormous quantities of lava, ash, and toxic gases into the atmosphere over relatively short geological time periods. The scale of this volcanism is difficult to comprehend. Lava flows cover areas the size of modern countries, creating vast basalt plains that bury entire ecosystems beneath layers of molten rock. The eruptions continue for hundreds of thousands of years, pumping massive amounts of carbon dioxide, sulfur dioxide, and other gases into the atmosphere at rates that overwhelm the planet's natural buffering systems. As the volcanic gases accumulate in the atmosphere, the global climate begins to change in ways that stress the Triassic ecosystems. Temperatures rise rapidly as greenhouse gases trap increasing amounts of solar radiation. The warming climate disrupts weather patterns that have remained stable for millions of years, creating droughts in some regions and floods in others. Acid rain begins to fall from skies choked with volcanic ash and sulfur compounds. This acidic precipitation strips leaves from trees, poisons freshwater systems, and gradually acidifies the soils that support terrestrial plant communities. The lush forests that characterize the Triassic world begin to show signs of stress as their chemical environment becomes increasingly hostile. In the oceans, the effects of the volcanism create conditions reminiscent of the Permian crisis. The massive injection of carbon dioxide into the atmosphere leads to ocean acidification as the seas absorb excess CO2 from the air. The warming climate reduces the ocean's ability to hold dissolved oxygen, creating dead zones where marine life cannot survive. The crisis unfolds over hundreds of thousands of years, creating a slow-motion catastrophe that gradually overwhelms the adaptive capacity of many Triassic species. Unlike the sudden impact of an asteroid, this is a crisis of accumulating stresses that build over timescales longer than any individual organism's lifetime. Many of the magnificent reptile groups that dominated the Triassic world simply cannot adapt quickly enough to the changing conditions. The massive Rowisuchians, perfectly adapted to the stable Triassic climate, find themselves unable to cope with the rapidly shifting environmental conditions. The armored-etosaurs and long-snouted phytosaurs also disappear as their specialized niches vanish, along with the ecosystem that supported them. In the seas, the crisis eliminates many of the marine reptile groups that had flourished during the Triassic recovery. The elaborate reef systems collapse as ocean acidification dissolves the calcium carbonate structures that took millions of years to build. Many of the beautifully ornamented ammonoids that had diversified so spectacularly are reduced to a handful of surviving lineages. By the time the worst of the crisis has passed, roughly half of all species on Earth have vanished forever. Entire ecological communities that had taken tens of millions of years to develop are reduced to scattered fragments or eliminated entirely. The Triassic world, with all its diversity and promise, becomes another chapter in the fossil record. But even as we witness this destruction, we can observe the remarkable patterns of survival and opportunity that characterize all mass extinctions. The crisis that devastates so many Triassic groups creates opportunities for the survivors to explore new ecological niches and evolutionary possibilities. The dinosaurs, still relatively small and unspecialized at the end of the Triassic, find themselves inheriting a world suddenly emptied of many of their competitors. The ecological niches once occupied by Rowisuchians, etosaurs, and other large reptiles become available for colonization by new groups with different adaptations and strategies. In this post-extinction world, the dinosaurs begin the evolutionary radiation that will make them the dominant terrestrial vertebrates, for the next 135 million years. Their efficient metabolism, sophisticated respiratory systems, and behavioural complexity give them advantages in the recovering ecosystems that their predecessors lacked. The early mammals also benefit from the extinction, though they remain small and nocturnal for millions of years to come. The elimination of many competing groups provides opportunities for mammalian lineages to diversify and experiment with new ecological roles, laying the groundwork for their eventual dominance in the far future. The recovery from the end-Triassic extinction follows the familiar pattern of gradual diversification, an ecosystem rebuilding that characterizes all such events. New species evolve to fill empty niches, new ecological relationships develop, and complexity slowly rebuilds from the simplified post-extinction communities. This process teaches us important lessons about the role of extinction in driving evolutionary innovation. While the loss of Triassic diversity represents a genuine tragedy in the history of life, the opportunities created by that loss allow for experiments that might never have occurred in a more crowded biological world. The end-Triassic extinction also demonstrates the vulnerability of even the most successful and well-established ecosystems to rapid environmental change. The Triassic world had achieved remarkable stability and diversity, yet it could not withstand the stress of sustained volcanism and climate change occurring over geological short timescales. As we prepare to move forward through time to witness the next great chapter in Earth's story, we carry with us an appreciation for both the fragility and resilience of life. The end-Triassic crisis shows us how quickly established order can dissolve when environmental conditions change faster than organisms can adapt, yet it also shows us how life finds ways to rebuild and explore new possibilities even after the most devastating losses. The dinosaurs stepping into their empty Triassic world could not know that they were beginning one of the most successful evolutionary radiations in Earth's history. Their story reminds us that endings and beginnings are always intertwined, and that the survivors of one crisis carry within them the seeds of future abundance and beauty. As time flows onward through history, carrying us forward 135 million years beyond the volcanic twilight of the Triassic world. We arrive now at the end of the Cretaceous period, 66 million years ago, when Earth has become a stage for one of the most magnificent evolutionary spectacles in planetary history. This is the culmination of the age of dinosaurs, a world where giants rule the land, sea and sky, with an authority and diversity that will never be matched again. The planet spreads before us in breathtaking abundance and beauty. The supercontinent Pangaea has finally broken apart completely, creating the familiar outline of modern continents, though they remain scattered in different positions across the globe. Shallow seas cover much of what will become Europe and North America, creating vast inland waterways that teem with marine life. The climate is warm and equable, with no ice caps at either pole and tropical conditions extending almost to the Arctic Circle. Flowering plants have revolutionized the terrestrial landscape during the Cretaceous period, creating ecosystems of unprecedented beauty and complexity. Vast forests of magnolias, palms, and primitive oak trees stretch across the continents, their canopies alive with the buzz of newly evolved bees and the flutter of primitive butterflies. This partnership between flowering plants and their pollinators represents one of evolution's most successful innovations, driving an explosion of diversity that transforms both plant and animal communities. In these flower-rich forests live dinosaurs that have achieved a magnificence and variety that defies imagination. Massive sauropods like Argentinosaurus stretch over 100 feet from nose to tail, their long necks allowing them to browse on vegetation that no other herbivores can reach. These gentle giants move through the forests in small herds, their footsteps shaking the ground and creating pathways that smaller animals follow for generations. Sharing the landscape with these titans are equally impressive predators. Tyrannosaurus rex, perhaps the most famous of all dinosaurs, patrols the forests of western North America with jaws capable of crushing bone and teeth as large as railroad spikes. These apex predators represent the culmination of theropod evolution, combining massive size with intelligence, acute senses, and sophisticated hunting behaviours that make them perfectly adapted to their role as rulers of the terrestrial food web. But the diversity of late Cretaceous dinosaurs extends far beyond the familiar giants. Herds of duck-billed hadrosaurs fill ecological niches similar to modern wildebeest, their elaborate crests serving as resonating chambers for complex social communications. Armoured ankylosaurs lumber through the underbrush like living tanks, their backs protected by bony plates and their tails ending in massive clubs that can shatter the bones of any predator foolish enough to attack them. Three-horned triceratops gather in herds on the open plains, their impressive frills and horns serving both for defense against predators and for display during mating rituals. These ceratopsians represent one of the most successful herbivore groups ever to evolve, with dozens of species showing remarkable variation in horn arrangement and frill ornamentation. In the skies above these terrestrial giants, pterosaurs have evolved to enormous sizes and spectacular diversity. Quetzalcoatlus, the largest flying animal that ever lived, soars on wings that span over 30 feet, riding thermal currents with the grace of a modern albatross, despite being larger than a small airplane. These magnificent flying reptiles fill every possible aerial niche, from tiny fish-eaters that skim the surfaces of lakes to massive scavengers that patrol vast territories in search of carrion. The seas of the Cretaceous world are equally impressive, dominated by marine reptiles that have evolved to sizes and forms that rival any ocean predator in Earth's history. Mosasaurs, essentially gigantic marine lizards, patrol the shallow seas with jaws capable of crushing ammonites and other hard-shelled prey. Some species grow to lengths of over 50 feet, making them among the largest marine predators ever to evolve. Long-necked plesiosaurs glide through the deeper waters like underwater dragons, their four flippers propelling them with surprising grace despite their massive size. The largest species exceed 40 feet in length, and their fossils suggest complex social behaviours, including possible parental care of young. Swimming alongside these marine reptiles are sharks that have perfected their predatory lifestyle over hundreds of millions of years. The ancient lineage of sharks proves that sometimes evolutionary perfection is achieved early and needs little improvement, as these cartilaginous fish continue to thrive in the Cretaceous seas much as their descendants do today. The ammonoids have rebounded from their Triassic losses to achieve new heights of diversity and beauty. Their spiral shells develop increasingly complex suture patterns and elaborate ornamentation that makes them some of the most beautiful fossils ever discovered. These sophisticated cephalopods fill numerous ecological niches in the marine food webs, from small planktonic forms to giants with shells over 6 feet in diameter. On land, early mammals remain small and largely nocturnal, living in the shadows of the great reptiles but slowly developing the innovations that will eventually allow them to inherit the Earth. These proto-mammals experiment with different reproductive strategies, develop more sophisticated social behaviours, and refine the metabolic efficiency that will give them crucial advantages in changing environments. This late Cretaceous world represents perhaps the closest thing to a real-life fairy tale that Earth has ever known. Giants walk the land with the authority of living mountains. Flying dragons soar through skies painted with the colours of tropical flowers. Sea monsters patrol oceans that stretch from horizon to horizon. It seems like a world that could continue in its magnificence forever. But on this particular day, 66 million years ago, something extraordinary is about to happen. High above the Earth's atmosphere, invisible to the creatures below, a mountain of rock and metal hurls through space at speeds that defy comprehension. This asteroid, roughly 6 miles in diameter, has been travelling through the cold vacuum of space for millions of years, following an orbit that will intersect with Earth's path around the Sun. The asteroid approaches at a velocity of approximately 45,000 miles per hour, carrying kinetic energy equivalent to billions of nuclear weapons. Its trajectory will bring it down in what is now the Yucatan Peninsula of Mexico, but the creatures living in the late Cretaceous world have no way to anticipate or prepare for what is about to befall them. The impact occurs in an instant that changes everything forever. The asteroid punches through Earth's atmosphere in less than a second, its surface heating to temperatures hotter than the sun's surface, as friction with air molecules creates a fireball visible across half the planet. The impact itself releases energy beyond human comprehension, vaporizing the asteroid and vast quantities of Earth's crust in an explosion that dwarfs any volcanic eruption in planetary history. The immediate effects of the impact are catastrophic beyond imagination. A crater over 100 miles in diameter forms in seconds as the Earth's crust rebounds from the incredible force. Massive earthquakes radiating outward from the impact site trigger avalanches, landslides, and tsunamis that circle the globe multiple times. But even more devastating than these immediate effects are the longer-term consequences that unfold over the following months and years. The impact ejects enormous quantities of pulverized rock and debris into the atmosphere, creating a global cloud of dust that blocks sunlight across the entire planet. Within hours, a twilight darkness descends on the Earth that will last for months. The darkness brings with it a global winter more severe than anything in Earth's previous history. Temperatures plummet as the sun's energy is blocked by the atmospheric debris. Photosynthesis effectively stops as plants around the world are unable to capture the solar energy they need for survival. The bottom of the food web collapses, and the effects cascade upward through every ecosystem on the planet. The great dinosaurs, magnificent as they are, prove tragically vulnerable to these changing conditions. The massive sauropods, with their enormous appetites and metabolic requirements, find themselves in a world where their preferred food plants are dying or already dead. The powerful predators like Tyrannosaurus soon have nothing left to hunt as the herbivore populations crash. The flying pterosaurs, dependent on thermal currents that can no longer form in the cold, darkened atmosphere, lose their ability to soar efficiently across the landscape. Many fall from the skies as their food sources disappear and their energy reserves are exhausted. In the seas, the effects are equally devastating. The marine food webs, dependent on photosynthetic plankton, collapse as these microscopic organisms die in the sunless oceans. The great mosasaurs and plesiosaurs, at the top of marine food chains, find themselves in an increasingly empty ocean where their prey species have vanished. The beautiful ammonoids, survivors of previous mass extinctions, finally meet their evolutionary end. These sophisticated cephalopods, with their complex life cycles and ecological requirements, cannot adapt quickly enough to the radically changed ocean conditions. Within a relatively short period, geologically speaking, roughly 75% of all species on Earth disappear forever. The non-avian dinosaurs, those magnificent rulers of the Mesozoic world, are eliminated entirely except for the small feathered theropods that will eventually be recognized as the first true birds. But even in this darkest chapter of the Cretaceous story, life demonstrates its remarkable resilience and adaptability. The small mammals that have lived in the shadows of the great reptiles possess several crucial advantages that help them survive the post-impact world. Their warm-blooded metabolism allows them to maintain body temperature in the cold conditions. Their small size means they require less food to survive during the period of ecosystem collapse. Perhaps most importantly, many mammals have already developed behavioural adaptations that serve them well during the crisis. Their burrowing habits provide shelter from the harsh surface conditions. Their omnivorous diets allow them to survive on whatever food sources remain available, including seeds, roots, and carrion from the massive die-offs. Birds, as the direct descendants of small theropod dinosaurs, also possess key advantages that allow some lineages to survive the extinction. Their ability to fly gives them access to scattered food resources across large areas. Their relatively small size and efficient metabolism help them survive on limited food supplies. In the marine realm, smaller organisms generally fare better than large ones. Fish, being more adaptable in their dietary requirements, then the specialised marine reptiles managed to survive the collapse of marine food webs. Many invertebrate groups, particularly those with simple life cycles and broad ecological tolerances, weather the crisis and provide the foundation for post-extinction recovery. The recovery from the Cretaceous Paleogene extinction follows a now familiar pattern, but with some unique characteristics that set it apart from previous mass extinctions. The elimination of the dinosaurs creates an unprecedented opportunity for mammals to diversify and explore ecological niches that have been unavailable to them for over 150 million years. In the post-extinction world, mammals begin an evolutionary radiation that will eventually produce the incredible diversity of forms we see today. Early pioneers experiment with different body sizes, dietary strategies, and locomotive adaptations. Some remain small and generalised, while others begin the evolutionary trajectories that will lead to giants like elephants and whales. The flowering plants, though severely affected by the impact winter, recover relatively quickly and continue their diversification. The partnership between flowering plants and their animal pollinators, temporarily disrupted by the extinction, re-establishes itself and drives new rounds of coevolution. Birds, as the surviving dinosaur lineage, also undergo rapid diversification in the post-extinction world. Freed from competition with their non-avian relatives, bird lineages explore new ecological roles and evolve into forms ranging from tiny hummingbirds to massive flightless giants. The Cretaceous extinction teaches us profound lessons about the vulnerability of even the most successful evolutionary lineages to sudden environmental change. The dinosaurs had dominated terrestrial ecosystems for over 160 million years, yet they could not survive the rapid changes brought about by a single catastrophic event. At the same time, this extinction demonstrates the importance of adaptability and ecological generalization in surviving major crises. The organisms that survived the impact and its aftermath were generally those with flexible dietary requirements, broad habitat tolerances, and behavioural adaptations that allowed them to cope with rapidly changing conditions. As we reflect on this pivotal moment in Earth's history, we can appreciate both the tragedy of lost magnificence and the wonder of new beginnings. The great dinosaurs were truly magnificent creatures that achieved evolutionary success on a scale rarely equalled in the history of life. Their loss represents one of the most dramatic endings in the fossil record. Yet their extinction also opened evolutionary pathways that led ultimately to the rich diversity of modern life, including our own species. The small mammals scurrying through the post-impact world carried within their genes the potential for all future mammalian diversity, from the intelligence of dolphins to the majesty of elephants to the complexity of human consciousness. The story of the end Cretaceous extinction reminds us that change is the one constant in the history of life, and that even the most devastating endings can become the foundation for new and beautiful beginnings. As our journey through deep time draws to its gentle close, we find ourselves returning to the present moment, to this quiet evening where you rest in comfort and safety. We have travelled together through 4.5 billion years of Earth's story, witnessing 5 great catastrophes that each threaten to end the story of life forever. Yet here we are, the inheritors of an unbroken chain of survival that stretches back through countless generations to the very beginning of life itself. Take a moment to let this extraordinary fact settle into your consciousness like sediment drifting down through still water. Every breath you take connects you to the ancient atmosphere that dinosaurs once breathed. Every heartbeat echoes rhythms that first began in the primordial seas, where trilobites scuttled across muddy seafloors 400 million years ago. The very atoms that make up your body have been part of this story from the beginning, cycling through rocks and rivers, plants and animals, stars and space dust across the vast expanses of cosmic time. We have witnessed Earth walk to the edge of silence 5 different times, each crisis unique in its causes and character, yet all sharing the same fundamental challenge. Could life find a way to continue when the world itself seemed determined to end the story? Each time, against odds that defy calculation, the answer has been the same quiet, persistent yes that whispers through every living thing. In the Ordovician seas, we watched as ice locked away the oceans and poisonous gases choked the remaining waters. The beautiful trilobites and sea lilies that had built Earth's first great underwater cities found their world shrinking and dying around them. Yet in the deepest refuges, in the most sheltered corners of a hostile planet, survivors waited with infinite patience for better times to return. Through the Devonian crisis, we observed how abundance itself can become dangerous when Earth systems are pushed out of balance. The gift of nutrients from the first great forests became a curse that poisoned the seas and suffocated marine life. The magnificent armoured fish and coral reefs that had flourished in the warm oceans slowly faded like music played at ever softer volumes until only silence remained. But even in that silence, life held on, preparing for its next great symphony. The great dying of the Permian showed us catastrophe on a scale almost beyond comprehension. 90% of ocean species vanished as Earth itself seemed to turn against life, with volcanoes erupting for hundreds of thousands of years and poisoning both air and water. For a brief moment in geological time, our planet teetered on the edge of becoming completely lifeless, a dead rock orbiting an ordinary star. Yet somehow, in caves and deep waters, in isolated pools and hidden corners, life persisted through conditions that should have been impossible to survive. The end of the Triassic taught us that even recovery and renewal can be fragile things. The dinosaurs and their contemporaries had built a magnificent world from the ashes of the Permian catastrophe, creating ecosystems of unprecedented beauty and complexity. But volcanism struck again, and climate change proved that no success, however spectacular, is permanent. The great reptilian dynasties fell, making space for new experiments in living. Finally, we witnessed the most famous extinction of all, when a mountain fell from space and brought the age of dinosaurs to its sudden fiery end. In a single day, the magnificent tyrannosaurs and gentle giants that had ruled the Earth for over 160 million years found their world transformed into something unrecognizable. The darkness that followed seemed absolute, yet in that darkness, small warm-blooded creatures stirred and began the evolutionary journey that would eventually lead to us. What do these ancient stories teach us about the nature of existence itself? Perhaps the most profound lesson is that life and death, ending and beginning, destruction and creation are not opposites, but partners in an eternal dance. Every extinction we have witnessed cleared away the old to make space for the new. Every catastrophe became, in time, an opportunity for innovation and experimentation. The trilobites that dominated Ordovician seas for millions of years eventually gave way to fish and marine reptiles that could never have evolved in a world crowded with successful arthropods. The armoured fish of the Devonian made space for sharks and bony fish that proved more adaptable to changing ocean conditions. The mammal-like reptiles that perished in the Great Dying were replaced by dinosaurs that achieved levels of success their predecessors never imagined. Each extinction reset the biological clock, creating what scientists call an adaptive radiation, as survivors diversified to fill empty ecological niches. Life proved endlessly creative in finding new solutions to the challenges of existence, developing innovations that might never have appeared in a world without periodic catastrophes. But perhaps the most beautiful lesson from our journey is that resilience is not just a characteristic of life, it is life's fundamental essence. Every organism alive today, from the smallest bacteria to the largest whales, from the simplest algae to the most complex human consciousness, represents an unbroken chain of survival that extends back through every extinction, every climate change, every catastrophe that our planet has experienced. You are the direct descendant of survivors. Your lineage includes creatures that weathered the Ordovician ice ages, that survived the Devonian ocean anoxia, that endured the volcanic hellscape of the Permian extinction, that adapted to the climate chaos of the Triassic volcanism, and that somehow found shelter when the asteroid brought darkness to the Cretaceous world. In your DNA lies the accumulated wisdom of 4 billion years of survival strategies. Your cells contain molecular machinery that was perfected in ancient bacteria, learning to harvest energy from impossible sources. Your nervous system uses signaling pathways that first evolved in creatures exploring the earliest reef systems. Your immune system employs defensive strategies refined through countless encounters with changing environmental conditions. This inheritance is not just biological, but also philosophical. The Extinctions teach us that change is not something to be feared, but something to be embraced as the fundamental creative force of the universe. Every ending contains within it the seed of a new beginning. Every loss creates space for unexpected beauty to emerge. The dinosaurs could not imagine the mammals that would inherit their world, just as the mammals could not foresee the eventual evolution of intelligence, consciousness, and the capacity to contemplate our own place in the cosmic story. Each stage of Earth's history has given rise to forms of beauty and complexity that could never have been predicted from what came before. This perspective offers profound comfort in the face of our own mortality and the challenges of our daily lives. Just as life has found ways to persist through seemingly impossible circumstances for billions of years, so too do we carry within ourselves the capacity to adapt, to endure, and to find meaning even in difficult times. The Extinctions also teach us about the interconnectedness of all things. No organism exists in isolation. Every species is part of vast webs of relationship that connect all life together. The fate of trilobites was linked to ocean chemistry, which was influenced by climate patterns which were affected by ice sheet formation. The survival of early mammals depended on the extinction of dinosaurs, which resulted from an asteroid impact that originated in the distant reaches of the solar system. We are part of these same interconnected webs, linked not only to all other living things but to the rocks and atmosphere, the ocean currents and weather patterns, the cosmic radiation and solar energy that sustain our planet. Our actions ripple outward through these systems just as theirs ripple back to affect us. Perhaps most importantly, the Extinctions teach us about the preciousness of the present moment. Each of the magnificent worlds we have visited, the Ordovician seas with their jewel-like trilobites, the Devonian reefs with their armoured fish, the Permian forests with their diverse reptiles, the Triassic ecosystems with their early dinosaurs, the Cretaceous landscapes with their giants, each was beautiful and unique and will never exist again. Our modern world, with its incredible diversity of mammals and birds, its flowering plants and complex ecosystems, its human consciousness capable of contemplating deep time, is equally precious and equally temporary. Like all the worlds that came before, it will eventually give way to something new and different and beautiful in ways we cannot imagine. This knowledge invites us to approach our lives with both humility and wonder. Humility because we are part of something vastly larger than ourselves, temporary participants in a story that began long before us and will continue long after we're gone. Wonder because we have been given the extraordinary gift of consciousness, the ability to understand our place in this cosmic narrative and to appreciate the beauty of existence itself. As you prepare for sleep tonight, let your breathing slow and deepen like the rhythms of geological time. Feel yourself settling into the same peace that has sustained life through every crisis, every change, every challenge our planet has faced. You are part of an unbroken chain of being that stretches back to the first spark of life in ancient seas and forward to possibilities we cannot yet imagine. In your dreams tonight, you might find yourself drifting once again through those ancient worlds we have visited together. You might swim with trilobites in warm Ordovician seas, or walk with the early dinosaurs through Triassic forests, or feel the ground shake beneath the footsteps of giants in Cretaceous landscapes. Know that these are not just fantasies but memories encoded in the deeper structures of your being. You have lived through all of these worlds in the bodies of your ancestors. You carry their resilience in your genes, their adaptability in your cells, their persistence in your very existence. Sleep peacefully in the knowledge that you are exactly where you are supposed to be in this vast, unfolding story. You are the universe becoming conscious of itself, matter, learning to think and feel and wonder about its own existence. You are stardust that has learned to dream. The extinctions have taught us that every ending is also a beginning, every loss an opportunity for something new to emerge. As you drift off to sleep, trust in the same patient, persistent force that has carried life through every crisis our planet has ever faced. That force flows through you now, connecting you to the vast community of all living things across all of time. Rest easy knowing that resilience is not something you must earn or achieve. It is your birthright, woven into the very fabric of your existence. You're part of life's greatest success story, the continuation of an experiment that began in the depths of ancient oceans and continues in this very moment of your breathing, your heartbeat, your consciousness settling into peaceful sleep. Tomorrow will bring its own challenges and opportunities, just as it has for every generation of life that has preceded us. But tonight, you can rest in the profound knowledge that you carry within yourself the wisdom of 4 billion years of survival, adaptation, and renewal. If this gentle journey through deep time has brought you peace, if these stories of ancient resilience have reminded you of your own connection to the vast web of existence, consider sharing this experience with others who might also find comfort in knowing their place in the cosmic story. A simple like or subscribe helps these stories reach other souls who might need the reminder that they too are part of something magnificent and enduring. Sweet dreams, fellow traveller through time. May you sleep knowing that you are held by the same forces that have sustained life through every challenge, every change, every transformation our beautiful planet has ever experienced. The story continues in you, through you, because of you. Good night.